Hi, welcome to Lecture 9 for MATH336. Today we're going to talk about Section 1.8 on acceleration velocity models. And the main goal in this section is to discuss how air resistance can affect your acceleration and velocity models. So we're going to introduce air resistance into our models. Let's start with an example. So suppose we have a car that's starting from rest and its engine is providing an acceleration of 10 feet per second squared. So we've seen problems like this before, but now we're also going to add an element of air resistance as well. So the air resistance for this question is that we're getting a 0.1 foot per second squared deceleration for each foot per second of the car's velocity. So if the car is traveling 10 feet per second, then the deceleration will be 1 foot per second squared. Well, actually, deceleration will be 1 foot per second squared. And if we're going 20 feet per second squared, or if we're going 20 feet per second, then the deceleration will be 2 feet per second squared. Okay, so that's the idea. And it makes sense physically that when you're not moving, there's zero air resistance, and the air resistance will increase as your velocity increases. So if you're going much faster, then you're going to be experiencing much more air resistance. So this is a good way to model air resistance, is have it be proportional to the velocity. Okay, so let's have a look at this question. So here's a picture of the situation. So we have a car, so there's my car, and the engine is providing an acceleration in the forward direction of 10 feet per second squared, and the air resistance is providing a deceleration of 0.1 times the velocity. And this will also be in feet per second squared because it is also part of the acceleration. So that means that we have an acceleration that is, for the engine is 10. So this is 10 feet per second squared. And the acceleration given by the air resistance is going to be negative 0.1 times the velocity, feet per second squared. And it's negative because it's a deceleration as opposed to an acceleration. Okay, so let's bring in Newton's second law of motion, which says that force is equal to mass times acceleration. So what is the force that is being generated by this acceleration here? Well, let's take m to be the mass of the car. So the force that is provided by the engine is going to be the mass times the acceleration, which will give us m times 10. The force given to us by the air resistance will be the same m, the mass of the car, times the acceleration provided by the air resistance, which is going to be a negative acceleration. In other words, it's a deceleration. So that'll be m times negative 0.1 times the velocity. And in total, we will have a total force is the sum of these two forces. And when we add those forces together and factor out the m, we get this expression here. Okay, so now we have the total force. This is the mass of the car. And then this is the acceleration of the car. And the acceleration is given right here. It's the derivative of the velocity. So that is the acceleration the car is experiencing, and this v is the velocity of the car at each time. So we have a formula for this. It's given by this right there. We just calculated above. And then we have that's equal to MA. Now what's nice about this is that the M will now cancel from both sides of the equation if you divide both sides by M. And you're left with this equation right here. And of course we know that the A is the derivative of the velocity. And so now we get our differential equation. So A is equal to dv dt. And I just reversed the equation, but it's the same equation. Okay, so there's our differential equation now. And the question is asking us to find the car's maximum possible limiting velocity. Well, there's an easy way to do this, and maybe we'll check this again after we solve the differential equation, but an easy way to get the limiting velocity is to find out when the force given by the engine is equal to the force given by the air resistance. So when do those two forces equal? And that will give us a zero total force on the car. So that will be when we have that the velocity is no longer changing, right? So in other words, there's a zero acceleration on the car. When the velocity stops changing, this is when those two forces are balanced out. So let's go ahead and use our differential equation. We have 10 minus 0.1 times v is equal to 0. And now we can just solve that equation. And we get that v will be 100 feet per second. So that means that the limiting velocity is 100 feet per second. Okay, so it will not be possible to go faster than that velocity. And you'll see when we solve the differential equation, we'll get the formula for v of t, and then we can integrate that and get the formula for the position x of t. And we'll see that indeed if you well, I guess with the velocity, when we take the limit as t goes to infinity, we'll see that the limit will be equal to 100. So we'll see that in a bit. Okay. Next question. It says, here we go, I'll just move this up here. It says, find out how long it takes the car to attain 90% of its limiting velocity. So now we know that would be 90 feet per second, and how far it travels while doing so. Okay, so we'll have to solve our differential equation. So let's write that down again. So dv dt is equal to 10 minus 0.1 times v. Okay, so there's a couple ways to solve this equation. One way is to observe that it is separable. That's probably the easiest way to do it. And it's also a linear equation as well. So we could solve it as a linear equation. But let's just use the separable approach. So a separable equation, we separate the variables like this. Like that. I'm just thinking now it might help to multiply both sides, or let's see. What we do? Well, let's just leave it like this. I was just thinking there's a way to get rid of that 0.1, but yeah, let's just leave it like this. Okay, so integrate both sides, and then we're going to have on this side, we'll make an educated guess that it is going to be a logarithm of the denominator. But now we have to think carefully. If we take the derivative of that logarithm, we're going to get this 1 over this, which is what we want here. And we'll also get times negative 0.1, but we don't have a negative 0.1 there. So to get rid of that, we need to divide by negative 0.1. Okay, and this will be t plus c1. Okay. So now let's multiply both sides by negative 0.1. That'll also be negative 0.1 times c1. And we'll take the exponential of both sides. So that will be e to the negative 0.1. Well, I'm going to rewrite that actually. So that is going to be negative t over 10. And then we'll also have times e to the negative c1 over 10. Get rid of the absolute values. The absolute value goes away and we get plus or minus this constant times e to the negative t over 10. And then we will subtract 10 from both sides. Let me just call, I don't want to rewrite this thing again here, so let me just call this thing, let's see, make a copy. So this thing will be C2. So I'll just make a note of that there. So C2. So C2 is equal to, let's see, C2 e to the negative t over 10. Oh yeah, and I'm subtracting 10 from both sides. Okay, there we go. And just make a little bit more room here. Okay, and now divide both sides by negative 0.1. And that will give us v is equal to c2 divided by negative 0.1 times e to the negative t over 10 minus, well actually that'll be plus, and that'll be 100. Oh, there's that 100 that we were expecting to see at some point. So that's the limiting velocity. Okay, and now I'm going to let C3 be equal to this C2 divided by negative 0.1. Okay, so V of t is equal to, oh actually I'll call that C. I'll just call that C. C e to the negative t over 10 plus 100. There we go. So there is our formula now for the velocity, taking into account some air resistance. And as I promised, if we look at this now and take the limit as t goes to infinity, we'll see why it's called the limiting velocity. Because when you let t go to infinity, this exponential will go to 0. So we'll get c times 0 plus 100. And again, we get 100 as our limiting velocity. So there again is the evidence that gradually we're going to increase our velocity toward 100. So according to this formula, we'll never quite get there because this will always be, so actually this C, we should probably, so I'm just trying to think here. So I guess this is always positive. Is that right? Did I make a mistake? I guess it depends. Maybe it depends on what your initial velocity is. Oh yeah, so maybe we should take that into account. Okay, so let's do that initial velocity. So our initial velocity was 0. So let's write that in here. So v of 0 was 0. So our initial velocity was 0. Okay, so let's put that in, and then that will give us the value of c there. So v of 0 equals 0. So that tells us that we have 0. Oh, let's write it in the same order. So c times e to the 0, which is 1, plus 100. Aha, okay, so this is 0. So that means, yeah, the c is going to be negative 100. Okay, maybe I should have done that. Well, anyway, so that's fine. Okay, so let me just add a page in here. There we go. Okay. And now what do we want to do here? So what do we want to do? So we do have the formula. Yeah, let's just write down the formula. So now we know that the formula is going to be v of t is equal to negative 100 e to the negative t over 10 plus 100. Okay, so there's our final version after using the initial condition. Okay, so as I was saying, so actually this term here, it's always going to be negative because this term is always something positive. So something positive times something negative. So that's always going to be negative. So we'll never actually be equal to 100, but we will approach it in the limit. So that's why it's called the limiting velocity. Okay, great. So what was the question asking? So it wanted to know how long does it take for the car to attain 90% of its limiting velocity? Okay, so we can attain 90%. So we won't attain the limiting velocity exactly, but we can attain 90% of the limiting velocity. So when will that be? So car attains 90% of limiting velocity when v of t is equal to 90 feet per second. Okay. Okay, great. All right, so we can solve this. So that's that is 90% of the limiting velocity. So 90 feet per second. So let's find out when that will occur. So we will get negative 100 e to the negative t over 10 plus 100 is equal to 90. Okay, so subtract 100 from both sides and divide by negative 100. So I'll give me negative 10 on the right. So I'll have negative 10 divided by negative 100. Okay, so take the log of both sides. So negative 10 over negative 100, that's 10 over 100, which is 1 over 10. So yeah, let's leave it like that. So 1 over 10 is, okay, so I'll take the logarithm. 1 over 10 will be 10 to the negative 1. So I'm writing it like that because then I can take that exponent out with using the logarithm rule. So I'm going to take this exponent and I'm going to put it out front according to the rules of logarithms. And I'm going to multiply both sides by negative 10. So that gives me my final answer. So that will be 10 log 10. So there's the final answer. And I suppose we should compute that, see what that is. Okay, so 10 times log 10. 23, so this will be 23.000 So it's like 0 to 5 and so on, something like that. So it's about 23 seconds. So therefore, car attains 90% of limiting velocity after about 23 seconds. All right, perfect. Okay. So then what was the other question? The other question is, how far is it going to travel while doing so? So how far has it traveled at the moment that it attains 90% of its limiting velocity? Okay, let's figure that out. In order to do that, we're going to need to take this equation here, and we are going to integrate that. Okay, so there's our equation, and we will have x of t will be given by the integral of this. And then there's going to be a constant, some other constant. Okay. Add a page. Okay, so we're going to integrate this. It doesn't look too bad to integrate. Let's see. So x of t will be the integral of that. So that will be negative 100. And then to integrate that, we're going to, let's see. So if we took the derivative, it would be multiplied by negative 1 over 10. So to cancel that, we will need to multiply by negative 10. And then this will be 100 times t, and then plus c. Okay, so let's just check if I take the derivative of that, do I get the right thing? So if I take the derivative of this term here, so I'll have this, and then I will have this, and then I need to multiply by negative 1 over 10, which will cancel that. Yeah, so that works. So I get this, and if I take the derivative of this, then I definitely get 100. Okay, perfect. So this is correct. And let's simplify that. So we'll have 1,000 e to the negative t over 10 plus 100 t plus c. And we're going to be starting at 0. I guess we should write that up here. So x of 0 is equal to 0. So what does that imply? So we will have 1,000 times e to the 0 is 1 plus 100 times 0 plus c is equal to 0. So that means that c is equal to negative 1,000. Okay, so therefore x of t is equal to 1,000 e to the negative t over 10 plus 100 t minus 1,000. All right, so there is our distance traveled at time t. And now we want to find out how far did we travel in this 23 seconds, or this is the actual exact answer here. So we want to use that value. So we're going to plug in t equals 10 log 10 into x of t, and that will give us our distance traveled in feet. Okay, so let's plug that in here. So x of 10 log 10 okay, so we have 1,000. I'm going to call this exponential of negative 10 log 10, and then that thing is divided by 10. Let's see, let's just make this look a little bit nicer. So move that up. And then we have plus 100 times 10 log 10, and then we have minus 1,000. All right, so this 10 cancels that 10. So we'll have the exponential of negative log 10, which is also known as the exponential of log 10 to the minus 1. So I'm going to take this minus 1 and I'll put it in here. And then I'll cancel these the exponential and the log. So this whole thing ends up being 10 to the minus 10. So that'll be 1,000 times 10 to the minus 10 plus 1,000 times log 10, and then we'll have minus 1,000. Let's just move this over. Minus 1,000. Okay, so this will be like dividing 1,000 by 10, so that'll be 100. And then 100 minus 1,000, that'll be negative 900. So we're going to finally get 1,000 log 10 minus 900. So that's probably a good expression to leave it at. So that's the exact answer. 1,000 times log 10 minus 900. And that will be about 1,400 feet. So we're going to get 1402.58 and so on. So that's how many feet. So therefore, the car traveled about 1,402 feet to attain 90% of its limiting velocity. And there we have it. Okay, great. Okay, I just quickly checked the answer in the back of the book, and of course they actually round this up, right? So that was probably a good idea. So instead of saying 1402, we should probably round it up. So it's actually 1403. Okay, so 1403. That makes more sense. All right, so let's continue. Okay, so now let's talk about vertical motion. So with vertical motion, again, we have two different things that are involved in the acceleration of the object. So instead of having an engine giving us acceleration, we have acceleration due to gravity. And that will be a downward acceleration. So we have acceleration due to gravity right there. So there's our, and that'll give us a force going down. And we know what that is. That's going to be mass times acceleration. And that will be, of course, it's acceleration going down. So that will be negative g, where g is given by about 9.8 meters per second squared, or about 32 feet per second squared. Okay, so that's the acceleration due to gravity. And then we also have an acceleration due to air resistance, and that will be a vertical in the case that we're going down, we're getting a vertical acceleration due to air resistance. And that will give us some force here due to air resistance. And just to note, if the mass is moving up, then in that case, if we're going up, then the force due to air resistance will be down. So that will be causing a further deceleration. So if we're going up, then we're getting a deceleration due to gravity and also a deceleration due to force, due to the air resistance. Okay, so we'll have to keep that in mind. All right, so let's have a look. So there's two possibilities we're going to consider. The first one is air resistance is proportional to velocity, which is very similar to the example that we just did with the car. So in that case, the air resistance was proportional to velocity. Now, this is a good model at low velocities. To use this model. It's a very simple model, and it's good for low velocities. However, if you were to think about, analyze like what is the actual force that is provided by air resistance, and how does it relate to velocity? So there's a kind of a mental experiment that we could think of. If we are falling through the air at a certain velocity, and if we double our velocity, that means that we're going to be displacing about twice the amount of air. So that means that the air resistance is going to provide us with twice as much, we'll get twice as much air resistance due to the fact that we're displacing twice as much air because our velocity is twice as fast. In addition, we're going to be hitting that air with twice as much force as well. So that air will also be providing another multiplier of 2 amount of force because we're hitting it twice as fast. So we're displacing twice as much air and we're hitting it twice as fast. That means that air resistance should be proportional to the square of the velocity. So if we're going twice as fast, we should get 4 times as much air resistance. So that's just, that kind of makes sense. And we will look at that model in the next step. But for low velocities, actually this linear air resistance is going to be pretty good. And there's an example in the book where they look at both models, and you'll see that I think they're doing it for like a crossbow bolt. So they shoot a crossbow up in the air, and then they look at what these two different models say. And they show that actually if you plot the two solutions, visually they're basically the same. And the values that they get are just slightly different. So that's why at low velocities, this is going to be a good model. Okay, so let's go through this. So in this case, the force due to air resistance is going to be negative rho times v. So why the negative sign? It's because if we're going down, that means that our velocity is negative, right? Because our y of t is decreasing, and so that means our velocity, which is the derivative of y of t, will be negative. So if v is negative, but the air resistance is a force going up, we need this air resistance to be positive, right? So when this is negative, we need to multiply by negative in order to ensure that our air resistance acceleration is positive. And if we're going the other direction, if we're going up, that means our velocity is positive, but we're getting a deceleration due to air resistance. And so that means that the air resistance should be negative in that case. Okay, so that's why we have a negative sign there. And we're taking this rho to be a positive scalar. Okay, so going through the Newton's second law again. So we have a force due to air resistance. This will be the mass times the acceleration due to air resistance. And that gives us this formula for the air resistance. And of course, we have this formula for the acceleration due to gravity, or the force due to gravity. So the total force on our mass that's falling is going to be the force due to gravity plus the force due to air resistance. And if you plug everything in, so we get the mass times acceleration is equal to the negative mass times the acceleration due to gravity, and negative m times rho v, that's our air resistance. And again, we have the mass everywhere. We can divide both sides by mass, and a is equal to the derivative of the velocity. So a is equal to dv dt. So we get our nice solution here for our model of vertical motion. Okay, so it looks good. And again, we have a linear and separable equation. So we could solve it either using separation of variables, or we could solve it as a linear first order differential equation. So this rho that models how much air resistance we're experiencing is called the drag coefficient. And so, for example, if we're falling with a parachute, we'll have a very small drag coefficient, so something like 0.15. And if we're falling without a parachute, it'll be like 10 times as much. So we'll have a larger drag coefficient. Now, what about terminal velocity? So terminal velocity, that's like the limiting velocity that we're looking at with the car. Terminal velocity is given by when the force due to gravity and the force due to air resistance balance out. Or another way of saying it is it's when we're having a zero change in rate of change in our velocity. And so we can just take our differential equation here, and we can say when is that equal to 0? So we solve for v, and we will get this formula for v. And we're going to refer to this as terminal velocity. We represent it as v sub tau, and it is negative g divided by rho. So this is a really nice formula. What it tells us is if we're able to determine what our terminal velocity is, of course we know what g is. So that's 9.8 or 32, depending on your units. That will allow us to calculate what rho is. So I guess I might as well write this in here. So another way of saying this is that rho, this drag coefficient, is given by the, let's see, move that up there, move that down there. So that'll be negative g divided by the terminal velocity. So there is the formula for this drag coefficient. So it's just computed based on your terminal velocity. Okay, so all right. So let's solve this differential equation. So as we mentioned, it is a separable differential equation. So we can just solve it the way we were solving the other one before. And V naught will represent our initial velocity. Okay, so we separate the variables. We move this down here, and we move the dt up here, and then we integrate both sides, and we get this. Okay, so proceeding like we did in the example. So thanks to that example, we're pretty familiar with what's going on, even though everything here are just kind of symbols. So there's a lot of symbols everywhere. But just remember, some of these are just constants. So, but it does look pretty bad. Anyway, so it's the same idea. We guess what the integral of this should be, and we know it should be like log of the absolute value of this denominator, and then we correct it by multiplying by -1 over rho. And if you take the derivative of this, you'll see that we do get exactly that. And the integral of the right-hand side is t plus c1. And we multiply both sides by -rho. So we get -rho t and then minus rho c1. Take the exponential of both sides. So the log goes away over there, and we get e to the -rho t, and then times e to the -rho c1. Removing the absolute value gives us a plus minus here. And then we're going to replace this whole constant with C2, which I mentioned over here. And let's see, what else do we do? Okay, so we're going to add G. We're going to move that over there. So we get plus G. And then finally, we divide both sides by this -rho. And I'm going to represent C2 divided by -rho. That will be C. So I put a C there. And we're dividing by this plus G by -rho. So we get this -G over rho. Okay. And next thing we do is we take our initial condition. So our initial condition says that our velocity at time 0 is v0. So we plug 0 into this equation, and that will give us e of 0, which is 1. So we get c minus g over rho is equal to v0. And that gives us c is equal to this. Now, we're getting a lot of these like negative g over rho, and here's another g over rho. And recall that actually our terminal velocity is given by -g over rho. So we can actually just replace all these instances of g over rho with using this terminal velocity. So our final solution is that we have our initial velocity minus our terminal velocity times this exponential, which is controlled by this drag coefficient. And then we have our terminal velocity here as well. And if we look at the limit of this velocity as t goes to infinity, this term here will approach 0. And so we get this thing times 0 plus the terminal velocity, and that gives us our terminal velocity. And so that makes a lot of sense. So we're going to be approaching our terminal velocity in the limit. So remember that this term will be negative. Well, I guess it depends if your initial velocity is faster than your terminal velocity or not. I guess that would be possible. But let's think of the case where our initial velocity is slower than our terminal velocity. And so this thing will actually be negative. And so we'll be gradually approaching our terminal velocity. Okay, but never actually achieving our terminal velocity. So just in the limit, we have this terminal velocity. All right, so let's look at an example where we use these ideas to look at an interesting account from a newspaper of a paratrooper who survived a training jump from 1,200 feet when his parachute failed to open, but it did provide some resistance by flapping unopened in the wind. So there's some sort of drag coefficient that's between like an opened parachute, which provides a lot of drag, versus a having no parachute at all, which would provide, you know, much less drag. So it's somewhere in between those two extremes. So it did provide some resistance, and in the end, the unfortunate paratrooper who did survive, but they did estimate that he hit the ground at about 100 miles per hour, which is not good. But and they say that he was falling for only 8 seconds. So now we want to test the accuracy of this account. So let's, you know, say we don't really believe this. We read this newspaper article and we're like, does that actually make sense that he was only falling for 8 seconds? So we're going to use our model for air resistance here. So our model for vertical motion, we'll use this one because this is not really fast enough to have to worry about using the more complicated model for air resistance. So we'll use this simple model, and we will determine this drag coefficient, assuming that his terminal velocity was 100 miles per hour. Okay, so the first thing we'll need to do is convert this terminal velocity into feet per second. Feet per second. So we'll need to convert this into feet per second. Okay, so I have to admit, actually, I'm from Canada. I don't know if I've mentioned this before, but maybe you can tell because I'll refer to the letter Z as Z. So let's see. I have to convert miles into feet. Okay, 1 second. I need to look this up. I'm not sure what that is. 1 second. Okay. So I looked it up. 5,280 feet per mile. I'm sure everybody knew that in this class, but I'm used to using kilometers and meters. So okay. So let's do this. So we have 100 miles per hour, and we need to multiply that by 5,280 feet per mile. So then this miles will cancel with that one. And we also need to multiply by the number of hours per second. So then that will cancel this and that. So 1 hour has 3,600 seconds. Okay, so let's calculate all that stuff. I'll erase this. So this will be 100 times 5280, and then divide by 3,600. And that is, the exact value is 440 over 3 feet per second. And what is that? So that's about 146.66 and so on. 6 repeated forever. Okay, so that's how many feet per second. So that's the terminal velocity. So it's about 147 feet per second is the terminal velocity. And now we can determine what is the drag coefficient. So remember, the formula for terminal velocity is this, and so therefore the drag coefficient is given by -g divided by this terminal velocity. So our drag coefficient is going to be -32 because we're using feet in this problem, and then we're going to divide that by this terminal velocity, which is 440 over 3. Okay, so 32 divided by 440 over 3, and that will be precisely negative 12 over 55, and that will be, let's see, so that's about 0.218 and so on. So about 0.218. So that is indeed between those two values of the drag coefficient that we looked at before. Without a parachute, I think it was 0.15, and with a parachute, it's like 1.5. Maybe I had those backwards. Let me just go up and have a look. Where did I write that down? Oh, here it is. So with a parachute, maybe I have those. I might have those in the wrong order, which would be unfortunate. Let me just double check. So with a parachute, 1.5. Okay, with a parachute, it's 1.5. Oh, okay, so I do have these in the wrong order. Okay, so let me swap these. Okay, so with a parachute, 1.5, without a parachute, 0.15. And in this example of this paratrooper, it was about 0.218. So a little bit more than falling without a parachute. Okay. I'm glad we checked that out. So there's our drag coefficient right there, 0.218. And now what do we want to do? So we want to find out how long it took the paratrooper to fall 1,200 feet after, so how long did it take? Did it take 8 seconds, or was it some other value? So let's compute the actual time based on this model for how long it took the paratrooper to fall these 1,200 feet. Okay, so what shall we do? I guess we could take our formula for the velocity right here and just plug everything into it. So let's grab this. And put that right here. So there's our model for the velocity. So if we plug everything in, the initial velocity was 0. The terminal velocity was 440 divided by 3. The drag coefficient is negative, it was negative, let's see. Oh, terminal velocity. Oh, this is the terminal velocity going down. Oh, yeah. Okay, so these should be negative. So we should have negatives in here. That makes more sense. Okay, so then, so this will be negative 440. Yeah, so that becomes a plus, and this goes away. Well, I mean, we could keep it there, but there's a negative here. And so this actually becomes, yeah, okay, that's better. Okay, so it's 12 over 55. All right, perfect. So let's see. So now we have negative 12 over 55 t, and then plus this terminal velocity, which is negative 440 over 3. Okay, so there is our formula for the terminal velocity. And I guess we could simplify this a little bit, we could write it like this. 440 over 3 times the exponential of negative 12 over 55 t minus 1. So just factoring out that 440 over 3. Okay, great. So we need to integrate this to compute the y of t. So y of t will be the integral of v of t. And then the initial height was 1200. So that is our initial condition. So let's go ahead and integrate this. So that'll be 440 and then times the integral of that stuff on the inside. So the integral of the exponential, so this will be the exponential. If I take the derivative of that, I'd multiply by negative 12 over 55. So I need to cancel that out by multiplying by negative 55 over 12. And then this integral of minus 1 is minus t. And then we'll have a plus c. And let's use our initial, oh, let's simplify. We could simplify that. 440 over 3 times 55 over 12. Okay. So that will be negative 6050 over 9 times the exponential of negative 12 over 55 t minus 440 over 3 times t plus c. Okay, so now let's use our initial condition. So when I plug 0 in here, this will be the exponential of 0, which is 1. So that will give me negative 650 over 9 minus 440 over 3 times t plus c is equal to 1200. So let's make a little more room for this. So that will be equal to 1200. Let's see. Just trying to think what's the easiest way to deal with this. I guess I'll just, I have to put, okay, I put 0 in. So this term actually goes away. That makes it a lot easier. Okay. There we go. So C is going to be equal to 1200 plus 650 over 9. $650 over 9. Okay, so that is 16,850 over 9, which is also known as about 18. So it's about this. So it's actually 0.2 repeated forever. We'll just write it like this. 2, 2, and so on. Okay, so those are the digits of C. And now what we'll do is we're going to solve for when is y of t equal to 0. So that's what we need to solve. So let me just add a page to the notebook. Okay. So therefore, what is our final expression, so it is this, copy that, put that right here. So that's what it is. It's pretty horrendous. And then this constant c is also pretty nasty. So here it is, 16,850 over 9. And we want to solve y of t equals 0. And we want to solve that for t. Now, this is not an easy thing to do. So I think we're definitely going to want to use GeoGebra to solve this. So we're going to solve using GeoGebra. So we'll see how that works. So let me switch over to GeoGebra and then we'll solve this. Okay, so here we are in GeoGebra. So we're going to start the calculator. Great. So I guess we have a couple options here, how we want to solve this y of t equals 0. We could enter in this expression directly, but it might be interesting to, let's see, where should we start with this? We could start with the original differential equation and enter that in and see what happens. So our original differential equation was that we want to solve the ODE, which is minus g minus rho. I wonder if you can do rho, no. Okay, let's back out of this. So maybe instead of rho, I'll just call it r. I don't know how to type rho in this, and then times, I guess we have to use y. Okay, so that's what it is. Okay, so we don't like this stuff. So G is 32, and R, which is our rho, so we calculated rho to be 12 divided by 55. Oops. 12 divided by 55. Okay, all right, that's right. And then V naught is equal to 0. Oh, let's just enter it this way. So V is equal to V naught minus V t. Oh, we have to compute VT. So VT is going to be equal to negative G divided by rho. There it is. Yeah, that's the value we wanted. So that is our terminal velocity. And then so V of t is equal to V naught minus VT times the exponential of negative r times t plus the terminal velocity. Okay, so that is our velocity being plotted over there. And now we can do the solve ODE, where we're going to integrate. So dy dt is equal to V of t. And we want to start with, at time 0, we have a height of 1200. Okay, so that's not going to work. All right. Let's see. Maybe I could just enter this directly. V naught minus vt times the exponential of minus r, and let's put x in just because I think GeoGebra prefers x and y's, plus vt, and our initial condition is 0 and 1200. Okay. Very strange number appearing there. Probably has to do with this r, which is 12 over 55. 12 divided by 55. There, that's better. Oh, that is our answer, right? Let me see. Yes. Yeah, that's our answer. Okay, so this is the thing we want to solve. So we want to solve this. So let's do solve. So I just want to solve when f of x is equal to 0. So I could just solve that. Okay, and it gives me, oh my goodness, it gives me two possible values. Maybe, is there an n solve? There we go. Okay, so the first value, so that's a numerical solve. That's what n solve means, numerical solve. Whereas this one was giving me like the exact solution. And it has this like Lambert W, which I don't know what that is. So the first x that it gives us is a negative value, but we're looking at positive time. So that would be this value right here. Let's see, let's move this over. Right there. So it's about 12, so I'm just going to write this down. So it's going to be, it's like 12.46 and so on seconds. Okay, so there's our answer. So there's probably other ways to do this in GeoGebra. I think I went kind of a little bit complicated here. I didn't really need these like sliders and stuff. Anyway, so we got our solution. We probably could have just entered this formula indirectly instead of trying to do the solve ODE step. So that probably would have been easier to just take this and enter it in here and say n solve and then type this formula in, and that would work. Okay, so that's good. Let's go back to the notebook. Okay, we're back. I just had to tell a chipmunk to be quiet. Okay. I'm lecturing here. Go back in your hole. So he's quiet now. All right. So there is our answer. So it was about 12.46 seconds. So the newspaper reported that it took about 8 seconds, but according to our calculations, the actual time that the paratrooper was falling was about 12 seconds. So therefore, we calculate that the paratrooper fell for about 12.46 seconds. Okay, so there we go. Good. All right, so one more topic that I wanted to go through. So this is more of just a satisfy our curiosity. We're not going to work with this model because it is a more complicated model to work with, but let's talk about it because according to Newton, this is the correct model. So physically, this is actually a more reasonable model, but it is more complicated. So there's a bit of a trade-off here. So if we look at air resistance proportional to the square of the velocity, one thing that makes this more complicated is now we actually have two different differential equations that we have to work with. If we're moving upward, then the air resistance is going to provide a downward force. So we get a negative rho v squared. So it's just like the gravity provides a negative acceleration or deceleration. We also get deceleration due to the air resistance. And when we're going down, then the air resistance is going the other direction. So there we get a positive air resistance. Okay, so this is a better model for motion at high velocities, but it is more difficult to deal with. In this model, the terminal velocity we can get by taking that downward differential equation and setting it equal to 0, like that. So if we're traveling downward, then we're looking at when there is no change in our velocity with respect to time. Solving that for v, we get this. Now there's two different options, but since the terminal velocity should actually be negative because we're going down, so that's a negative velocity, we have that the terminal velocity is the negative square root of g divided by this drag coefficient. Okay, so if we were to solve this upward motion differential equation, then this is the formula that we would get. It involves tangent, and then there's a constant here, C1, which involves an inverse tan. And if we integrate that one more time, we get something like this. So there's a logarithm of an absolute value of a cosine in there, so more complicated. The downward motion is even more complicated. It involves a hyperbolic tangent, and then this constant here involves the inverse hyperbolic tangent of this. And the position function is given by the natural log of the hyperbolic cosine, natural log of the absolute value of the hyperbolic cosine. And in case you're curious what these hyperbolic trig functions are, they're actually just exponentials. So the hyperbolic sine of x is given by this, and hyperbolic cosine of x is given by this, and then hyperbolic tangent is just going to be the hyperbolic sine divided by hyperbolic cos. And so these 1/2 will cancel each other, and we get this formula for the hyperbolic tangent. So that's what we have here for the solution of the upward and downward motion, assuming that the air resistance is proportional to the square of the velocity, which is more physically reasonable, but definitely, as you can see, more complicated. You do not need to memorize these equations. So just for your curiosity, what it looks like, there you have it. Okay, so that is the end of the lecture, and that's actually the end of chapter 1. Thanks for watching.